We are lucky to have two outstanding speakers today, Alan Perelson and Fred Adler. Without further ado, I'd like to introduce Alan Perelson, who's our first speaker, and I'll turn the connection over to him. He's going to talk to us about his modeling, focusing on COVID and SARS issues, although perhaps we can persuade him to come back another time and talk about some of the many other viral systems that he's worked on. So without further ado, I will turn over the screen share to you.
Okay, well, thank you for inviting me. Here's my email address, and as this group knows or should know, I'm interested in hiring one or two postdocs on viral infection modeling and immunity. Currently, my group works on a number of viruses. HIV is our current one. We're very much interested in strategies for curing it, not only using antiviral therapy, but various modulation in combination with that. And all of the work that or 90% or 95% is always done in collaboration with either clinicians or experimentalists. So we're very data driven. Also, there's a big push now to try and cure hepatitis virus. That's a virus that infects the liver. There's about 300 million people that are infected with it. And just as in HIV, it's not yet curable. You can treat it with drugs, but it's basically lifelong therapy. There's a big push by pharmaceutical companies to come up with new classes of drugs, and we've been developing multiscale models that incorporate not only intracellular replication, but are also collaborating with experimentalists, modeling spatial spread of the virus, so analyzing biopsy samples. We also work on HIV, Zika, West Nile, and many of those things are winding down just because the HCV has basically been cured. Zika is not around so much. There's now monoclonal antibody therapy for Ebola. So much of our work in the last 6 months, like of many people in this field, has been devoted towards modeling SARS coronavirus 2. And the approach that I'll show you today and that we use is to use models driven by data. And what we try to do is see what the data can tell us. Occasionally we'll do purely theoretical work, and you'll see at least, I'll show you a snapshot of a stochastic model that was done, theoretically. We were using it to get some insights into what happens in early infection. And the exact form of the model depends on the data that we hope to understand. We just started a collaboration looking at in vitro experiments, testing combination drug therapy. There's non-innate models that have been very important, especially in the HIV work, but it's all used now in SARS, and mostly human data. So let me start with a set of equations that we derive for studying acute infections in the case of influenza A in humans. This is a form of what we call target cell limited model. There's T is target cells, cells that can be infected, I infected cells, and V is the virus. And this very trivial model actually can summarize quite data from human infection. We found one problem with it, in that it made predictions about the lifespan of infected cells that was too short. And we think the reason for that is we left out a very important part of the life cycle called the eclipse phase, which is the time from when a cell is infected till it actually starts producing virus. And that can be many hours to a day or more, depending upon the virus. So we've split the infected cell population into two subcomponents. The first one, I1, doesn't make any virus, and it goes into class I2, which are, quote, productively infected cells and makes virus. Other models that we've worked on, and I won't have time to summarize, is you can actually use this as a delay equation with a distributed delay. You can approximate that with a Erlang function, an Erlang distribution. You can do other fancy things with it. But this simple one works for a lot of infections when we don't have much data, and particularly in vivo. When we think about therapy, or what our objective is to reduce the basic reproductive number below 1, just as in the case of epidemics. And for the model that I do, it's a very simple algebraic expression having a production of virus, infection of target cells, and then on terminators, way things get cleared, the virus gets cleared autonomously or by infecting cells, and infected cells die. So getting into data, so early in the infection, hospitalized patients, Singapore, were followed closely, and this group published the data for 18 patients, table with the actual PCR results in them. So it was very easy to do it. 5 of the patients were under therapy, leaving 13 to be analyzed in the absence of any therapy. The data points here are measurements. The solid lines is something we came up with from a very simple model, which you can see, roughly is in agreement with this data. It's a very simple model, in fact. It starts at time 0. We assumed a 5-day incubation period because data was only collected once patient was symptomatic. This work was done in collaboration with an ex-postdoc and now close collaborator, Jeremy Gage. We fit the data using a population approach, something in a program called models. We could estimate R0. Confidence interval is quite large because the data is rare. We got an estimate. The death rate of infected cells, really the first one who's been published yet, goes on in vivo. And it corresponds to productively infected cells producing virus for the low rate, which is very similar to what we see in HIV. But more than the reason for trying to get these parameters and looking at simple models was then we could add the effects of antiviral therapy. And unfortunately, we don't have good antiviral therapy yet, but we're trying to ask, can we repurpose drugs to do something? And the way we do that is we take parameters of the model that drugs might affect, like beta is the rate of infection, and that can be reduced if you use a neutralizing antibody, like the remdesivir cocktail that treated President Trump. Hydrochloroquine has been intimated to possibly influence infectivity. One can block the replication of the drug, which would reduce the amount of virus being produced. So we replace P by this 1 minus epsilon P, where epsilon is a parameter unknown that goes between 0 and 1. The idea being if epsilon is 1, it's a perfectly effective drug. And so we call this, or sometimes, and you could also modulate the viral clearance rate or infected cell rate with monoclonal antibodies. Jeremy has close connections with developing some of these drugs and had access to some PK data, pharmacokinetic data for a variety of possible treatments. We actually could then use the dose dependence. So this is meant to be the drug divided by the TC50 as we're getting the effectiveness. And here we were thinking of a 7-day course, and this is just an average effectiveness. If one had detailed PK data, you could actually do this as a function of time, and epsilon would be varying. What we discovered, which was not unsurprising, that wanted, for example, up the peak viral load by about 2 logs. Many people think that the amount of virus that you get near its peak is what drives symptoms. What this shows is what happens if we, in the simulations, if treatment is initiated at the day of infection, which is pretty much impossible to do. But then you can have fairly weak drugs would work well. But if you can think of doing this prophylactically. If you're married and your spouse gets infected and you immediately taking drugs. You initiate at the time of symptom onset, you can still do okay, but you need on average with a business or an efficacy of about 80%, which none of those drugs most likely obtained. And then if you wait till a few symptom onset, where most hospitalized patients are treated, in fact, you need a drug that you're 99% effective to have to drop the viral load or the area under the curve in any significant way. So a very simple analysis gave us some insight into why things don't work. Then we asked, could we use these drugs for prophylaxis? Since it looked again like from that simulation that if you started therapy at the time of infection, things might work better. However, we think that the infection started at very low amounts of virus. Some estimates are something like 10 infectious virus particles might be sufficient. So at that level, the model is stochastic. ODEs aren't appropriate at these very early stages. Convert the viral dynamic model into a stochastic model with various events that occur with the probability of them occurring at time being proportional to the rate constants. These can be simulated by a Gillespie algorithm, give rise to densities. But if we assume that the number of target cells stays constant in these early stages of infection, then it turns out that you can write a master equation and you can actually solve it analytically, at least for the probability that the process either goes extinct or it becomes established. We had done this previously in the case of HIV in a model without an eclipse phase, and one of my collaborators, Jessica Conway, did a more complicated model with the eclipse phase in it. It turns out if you don't, if the cells are assumed not to die during the eclipse phase, it has no effect on the probability of establishment or of extinction. And so it depends really only on the R0, which I had shown you before, and a quantity n called the burst size, the number of viruses made by an infected cell over its lifespan. And the lifespan in these models are R1 over delta, and this is the amount being produced, and also viral load. And you can then put in drug effectiveness just as before. You change the parameters such that, so for example, for a drug that reduces viral production, you replace P by 1 minus epsilon P. It changes the probability. Then you've done work a group, mostly done by a French postdoc who was in collaboration with Jeremy Gage, Peter Cousin at the Sorbonne, and we studied both analytically and then by stochastic simulations in case this target cell being constant was, just check it. And what you find is that there is a, what we call critical efficacy. If the drug efficacy is greater than some value, then the establishment probability goes to 0. And you can see that in these curves here, where this is just showing you the probability of being established as the drug efficacy goes down. 0 is sort of our baseline, there's no drug. And so we're in a parameter regime where, depending upon the initial amount of virus, the probability of establishment is very close to 1. So that's all theoretical. And again, it shows that it's possible to, not too effective, especially if used in combination, you can get the required critical efficacy down. And at the end, I'll give you the references. These are all on preprint servers, so I'm not really going to go into details. I just want to go quickly. This was a second paper that came out early, first in March, that also had hospitalized patients with COVID-19. What was interesting in this data set is two things. One, they were sampling in the upper respiratory tract, which is in yellow, no, in gray, excuse me, and then in sputum. So I had these patients cough, and it's thought to possibly represent what's going on in the lower respiratory tract and lungs. They also did some work in stool, which we didn't model. Again, this data was available. But the other nice thing is this group actually had done some epidemiological studies. Prior study showed that how this infection spread among these 9 individuals. They did contact tracing, and so the data that people were infected and who infected them were known. Instead of having an arbitrary incubation period, we actually could infer a real date of infection. Also, because we had data from both the upper respiratory tract, from throat swabs, and also in the lower respiratory tract, we made a 2-compartment model. So this is what I said earlier. We use the data to drive what we do, including in a model. And this work was done with 2 ex-postdocs of mine who are now staff members at Los Alamos, Ryan Key and Rui Ribeiro, who's been back on the staff for almost 20 years, and we collaborate on most viral infection modeling. So again, a very similar model. Ruan calls cells in the eclipse phase E instead of I1 and I2, but it's really the same idea. And then we allowed the possibility of virus to move between these 2 compartments, is the way these were pulled. Also, we worried about the fact that you're sampling by these compartments. So if you're taking a throat swab, so you're only sampling a fraction of the virus. So there's another sort of unknown parameter. And the same thing when you sample sputum, you don't really get a direct measure of this. It's just a complication that you can look at. Took that model again, fitting to data in both the upper respiratory tract and the lower respiratory tract, and you can see the fits of this model to early days post-infection. And the data set actually goes on longer, and the fit of this model are not so good if we let it go longer. This is just a simple target cell model. And so to try to understand the longer term data, we recognize that immune responses start coming in somewhere in this region post-peak. So we did, again, a very, very simple thing that we had done earlier in some work on influenza, and so an adaptive immune response might come in, say, somewhere in this data set. We was guessing it around, and that could increase the death rate of infected cells. And there are various ways that this can occur, which you can read later at your leisure. But the technical thing was we said that there was an exponential increase now in the death rate. If you thought of antibodies, they start increasing exponentially around this time in typical patients. So we added target cell limited model with this adaptive immune response. Now we can get a reasonable fit to long-term data. And you'll note that the long-term data is all in the lower respiratory tract. So in these patients, the infection moved from their upper respiratory tract, nose and throat, becomes undetectable in most of these patients, but it seems to move into the lower respiratory tract and persist for patients about 3 weeks or more. The fits aren't perfect, as you can see, and we're sticklers for trying to do the best job we can. And so we worried a little bit about these extra points that were too high for our model. We decided we'd try to put in an innate immune response, which is known for basically stimulated work on interferon, IFN. Those of you who know interferon, it stimulates hundreds when it binds to its receptors, and in the case of virally infected cells, it can put them into something called an antiviral state, in which they're refractory to new infections. And so we allowed our target cells to interact with interferon and be driven into the refractory state. Refractory state isn't permanent, and so we allowed them to go back to being targeted. And we just said interferons released from infected cells, and it is lost in some ways, and it can be lost by going into cells, or it's lost by degradation. And you do the same thing in the lower respiratory tract. That model does a little bit better. As you can see, it's getting up a little bit better, but still not getting all the points. And so we were concerned a little bit about these things that look like extra peaks that may be coming up. So we said, let's try another thing. And what we were thinking about is that from work that we've been collaborating with Amber Smith, who studies influenza in the lungs of mice, which she has shown that as time goes on, you can actually see that the infection spreads spatially in the lung. And that you could either think of it as getting from one of the lobes of the lung, which, in case you don't know it, your lungs actually have 5 different lobes. It might get into another lobe, or it might just spread and find new target cells. So again, we keep things simple. And so we did what I call a poor man's model, or poor man's range extension. We just assumed that at some point in the infection, that the virus enters a region where it can find new target cells. So we just basically did the injection of T sub n targets that appear in the lower respiratory tract at some time Tn, T sub T, and we had 2 more parameters that we had to fit. Of course, when you're doing model selection, you're going to be penalized because we have 2 more parameters. This gave, in fact, very good fits. It could explain these other little peaks that were coming up. And so the best model that we came up with was a model, a basic target cell limited model with an adaptive immune response and having these new target cells. You can add the innate response, but in fact, it gets penalized by the AIC quite severely, and it doesn't lead to any significant improvement over these fits. We've done other things I won't show you. We added new target cells by just assuming for it locally. That also didn't do as well. We've looked at models where we just assume that de novo infection, that new virus, you can just breathe it in and it seeds new infection in the lower respiratory tract. That does almost as well as this. The fits look the same again, but it's being penalized by extra parameters. So let me stop. It was just a quick, very quick overview without going into great details of 3 projects. We actually have additional ones going on, but just to give you a flavor of the type of work we do, one can obviously build in much more complicated immune system responses, and that's in ongoing work. We're trying to do that, but it really requires, we think, data. We've been very critical of some of the models in the literature where people just put in cytotoxic T cells and have all sorts of rules about them, but there is no comparison with data. Thing with antibody responses or much more complicated innate responses. Anyway, if you're interested in more details, take a look at these papers. The first one was published. The other 2 are on the archive. And I'm happy to take questions, or presume we're running late and we probably need time for Fred. So let me stop sharing and turn it over to you, James, or to Fred.
Thank you, Alan. No, we certainly have time for some questions, please. We can't talk too long, but it would be a pity not to have some questions from the audience. Sure. Please feel free to unmute. Try to keep your questions a little short, but please go ahead, Jacob.
So I have a question that's actually practical. I'm looking for the infectiousness period, but at the level of a function. That's like the person is less infective in the beginning, more infective at some point, then less. It seems that you're very close to this. Can you give a function of how much virus a person sheds according to time since infection?
So if you look, so I didn't say that, but in this last model, we did the upper and lower respiratory tract. We actually spent quite a lot of time sort of speculating about that very issue. So since we know something about who infected whom and when they did, we also know what the viral load was and it was co-transmitting. So what we've done is we look at the viral load profiles predicted by the model as we fit in the data. And then we asked, could we come up with a function for infectiousness that could mimic transmission? And we had a variety of criteria. Wanted something like 40% or something close to 40% possibility of asymptomatic or pre-symptomatic transmission was given in the literature. In addition to this, what we found is 2 things. One, we think the infectiousness is probably proportional to the log of the viral load, not the viral load itself. And secondly, the type of transmission function that we needed to use was a sigmoidal function of the log of the viral load. And there is some data in HIV transmission and influenza transmission that shows that these transmissions saturate.
Can I get hold of this function? Meaning,
yeah, it's in the preprint. So just go on that archive page, or send me an email and I'll email it to you.
Thank you very much. I'll put my email there. Thank you.
Okay, sure.
Fred, did you want to ask a question?
Yeah, just quickly, when you fit the data to that set of 8 or 9 patients, did you fit them each individually or did you treat them as random effects and fit them as an ensemble?
So we ended up fitting them individually. And that's just because we could do the short term, we could do as a random effects, the first 12 days they showed, so that we could do random effects. But when we do the long term, that was not very successful because there were great differences in the patients, so we fit those individually when we went to the long-term data. Because not every patient seemed to show both the long and what we think of as these other peaks, which was indicated by new sources or spread in the lungs.
Great. Any other questions for Alan?
I have just a quick one on the upper and lower respiratory tract data showing the presence stay much longer in the lower respiratory tract. Do you have a speculation of why that is? Are those cells that replicate the virus located more deep in the lung than in the upper respiratory tract? Would maybe be the
well, I mean, the lungs clearly are a much larger organ. And we think, that the virus can spread within that organ, somewhat slower. So continue to find, quote, new target cells is just one speculation. Also, as time goes on, immune cells are coming in to slow down the spread. so it can move somewhat slower for the target cells stay around longer to think is going, but those are only speculations.
Thank you.
Sure.
Okay, if there, I hate to cut off discussion, because it's so, but we should probably move on